So besides using k-way merge, another way to reduce the number of passes is if we can generate a longer run. If a run gets longer, we may generate less number of runs, right? And therefore need less number of mergings. Now let's look at this example. Again, we assume that our internal memory can hold 3 numbers only. And then how can we generate a run that is longer than 3? The solution is do heap sort. And still we start from loading the first 3 numbers, okay, and generate a min heap. And after calling delete min, we're supposed to write this 11 out to the result, okay, and then read the next element in, and the next element is 96. And what we do is we compare this new element with the one we have just deleted, all right, and if this element is larger than 11, it means that it can belong to the same run as this 11, so we count it in. All right, and next we're supposed to output 81, and we're ready to read in 12. But when we compare 12 with 81, we realize that this number is smaller than 81, which has been outputted, and therefore 12 cannot belong to the same run with 81. All right, but still, let's read 12 in. But 12 is not counted as part of this min heap. So the current min heap contains only 2 numbers. All right, and let's output 94 and read in 35, and output 96 and read in 17. And at this moment, we realize that the first run is done. So the first run contains 4 elements. And all those elements currently inside this heap belongs to the same run. Now let's adjust it into another min heap. All right, now continue to output 12. And then the next one will be 99. And since 99 is larger than 12, let's count it in. Next, output 17 and read in 28. 28 is larger than 17, so let's count it in. All right, output 28 and read 58, and 58 is also larger than 28, so again count it in. Output 35 and input 41. Output 41 and input 75. You see how it's working? Now output 58 and input 15. So 15 is smaller than 58, so it's impossible to include 15 into this current run. But still, let's continue to output, but 15 is not part of the current run. And we get 75 and 99, and finally 15 belongs to the last run. Now, here's a quick question for you. What if we swap 35 with 99? What's going to happen? Now, let's move back to where we were before 35. Okay, if this is not 35, if this is 99, what's going to happen? We have just outputted 94, right? And if the next number is 99, although 12 doesn't belong to the current run, but 99 can be included because 99 is larger than 94, right? So after we output 94, 99 can still be included into the current run. All right, this method is called replacement selection. And in general, the runs generated by this method is about 2 times m, where m is the size of the internal memory. So it will generally double the size of each run. On the other hand, of course, you can always carefully design the worst case. so that this method doesn't work. But practically speaking, whenever external sorting is involved, usually the input is nearly sorted. Okay, if that is the case, then this replacement selection method is quite powerful. The last topic is about how to minimize the merge time. Notice that when we do two-way merge, some of the numbers will be merged for several times, right? So for example, suppose we have 4 runs of length 2, 4, 5, and 15. How can we arrange the merging to obtain minimum merge times? Say if we merge 2 and 4 first, and then merge 5 and 15, then we're going to obtain 2 runs, one with the length 6 and the other one with the length 20, right? And during that merge, everybody is merged once. So the total time is going to be 26, right? And then we're going to have to merge these 2 runs into one piece, right? So there will be another 26. And the total merge time will be 26 times 2, which is 52. But can we get faster than that? The key is that for the large runs, we don't want to merge them again and again, right? Like this run with 15 numbers. We prefer to merge them only once, so to reduce the merge time. So how about this? Let's merge 4 and 5 and get a run of length 9, and then merge 9 with 2 and get 11, and finally merge 11 with 15 and get 26. So altogether we have the run time like 9 plus 11 plus 26. Altogether is 46, a little bit better than the previous result, which is 52, right? So does it remind you of anything? It's the Huffman tree, right? Hey, of course. If we order the mergings in the way we form a Huffman tree, like this, so the total runtime will be what? The total runtime will be proportional to the weighted external path length, right? In this case, it's just 2 times 3 plus 4 times 3 plus 5 times 2 and plus finally 15 times 1, which is 43. A little bit better than we merge 4 and 5 first. Alright, so to summarize, we introduce external sorting as a kind of application of merge sort and heap sort. It's based on merge sort, and we apply heap sort to generate longer runs in order to reduce the number of passes. And at the meantime, we can also use k-way merge to get it done. And we can carefully design the buffers in our internal memory to let input, output, and merging done in parallel. And we can use Huffman tree to further optimize the merging time.